Oh, hi there. Thanks so much for showing up for your math learning. It's Tutor Grant, and we're looking at question 25 of the 2025 Fermat test. And this question is rather challenging, but it's not insurmountable, and I'll show you how you can answer questions like these by being very careful and thinking about things like, well, first of all, the number 2025. We're first given this sequence where the first term is 1 and the next term is 3, and we create each following number in the sequence by taking the negative of the number that just came before. So it's better to think of that as just flipping the previous term's sign and adding it to the term that came before that one. So if we start 1, 3, our next one will be negative 3 plus 1 equals negative 2. And the next one would be negative 2 plus 3 will equal 5. And then you do negative 5 minus 2 is minus 7. Negative 7 plus 5 is 12. And we're going to use a calculator to build that out in just a moment. One thing that we're asked to do here, the thing that we're asked to do is consider the first 2025 terms in this sequence, and then ask if we square those, how many of those are divisible by 2025 itself. All right, let's talk about this idea, like an squared divided by 2025. Okay, I think you'll agree that we could write this as an, let's say the nth term squared divided by 45 squared. In which case you could say that, well, this is just an divided by 45 squared, okay? So that is to say, if the square of one of these terms is divisible by 2025, then the term itself is divisible by 45. Another thing we can do is really ignore the positive and negative signs that are showing up in our sequence, because even they still would be divisible. But even if you were worried about positive and negative, when you square stuff, it always becomes positive anyway. So those are strictly positive. So we are looking for which ones of these terms are divisible by 45. That's all we're looking for. Okay. Well, that should be easy enough. And how many of the first 2025 terms in the sequence are divisible by 45? Okay. So when you confront a problem like this, you have to know that there must be some way to investigate that sequence and find out that answer to that question. Okay? So if we're interested in divisibility by 45, we know that we're looking at divisibility by both 5 and 9. Okay, so that's why I've created this little chart. We're going to be interested in divisibility by 5 and divisibility by 9. And I'm showing divisibility by 3 here just to show a pattern. Okay, so getting out our calculator, I'm going to show you how you would do this on a calculator. But one thing to notice is, like, if I do 12 and make it negative, so negative 12 and minus another 7, I will get negative 19. But if these were both positive, I would have gotten the same thing. And the next thing I would be doing is doing 12 plus 19, which is in fact what I end up doing next to get 31. Like, the toggling positive and negative of the signs here is continuous, but it's irrelevant. So that's a little red herring that they put into the problem to distract us. We don't really need to worry about these signs at all. Okay, so I'm just going to erase my working there, and I'm going to show you how I would do this on a calculator and then build out the next few while I pause. So let's say we have here our calculator. Just move this over here. And so now we just go, okay, so I say 19 plus 31. I mean, we know what that is. Happens to be 50, so I write it down. 50. And then just do 50 plus the one that came before it, 31 equals 81. And then plus 50 equals 131. This would be how I would build it. And then later on, just to have them, I'll just go ahead and flip those negative. You can, if you doubt me, you can go ahead and investigate yourself and do this a little more carefully and find that I'm absolutely right. Okay, so I'm just going to pause the video for now and build out a few of these in sequence. Okay, so that was fun. So I just used the calculator to build out this list. And now let's investigate the list and see what patterns we find when we're looking at divisibility by 5 and by 9. Now, divisibility by 9, of course you need to be divisible by 3, but the divisibility test for 9 is you take the digit sum and see if it's divisible by 9. So while we're at it, let's take a look at the patterns in divisibility by 3, because actually this pattern is far more frequent, and it also contains something instructive about these patterns. Okay, so we're going to note that this one here is divisible by 3, this one is divisible by 5, this one is divisible by 3, this one is divisible by 5, and this one is divisible by 981. Okay, then we keep going and we find 343, really? 212, no. 555 is divisible by both 5 and 3. 898 is not. 3804 is divisible by 3, and 6155 is divisible by 5, and then 26073, we add all the digits together and that gives us 18, and oh, that one is divisible by 3 and 9. All right, and then we could keep going and find that this one is divisible by 5, and this one here must be divisible by 3. Yes, this one is divisible by 3. It has a digit sum of 30, and then that's it for our list. All right, so let's take a look at the patterns that we had. Oh, I didn't show that this one was divisible by 3. I should have, for the sake of showing these patterns. Notice that every fourth term, starting with the second term, is divisible by 3. And this pattern absolutely continues off to infinity. And this is the case with all Fibonacci style sequences. They all have this habit of having, this property of having their divisibility by 3 recur every 4 terms. Okay, it's just how they're built. I can prove to you why, but it'll be a very long video if I do that. So we observe that and we're like, okay, I believe that there are patterns. If I see patterns, there must be patterns. Okay, and then we note, okay, the fourth one, the ninth one, so in this case we are like, if we're looking at divisibility by 5, we have to add 5 each time, okay, to the term number. So 9 and then 14, so we add 5 and we get from 9 to 14. Our next one should be 19, and oh, look, it is. 19 was. And then the next one should be 24, and oh, look, it was. And if we had gone to 29, which we didn't, we were out of paper, it would have been as well. Okay, so that one, we're actually particularly interested in that, right? Because we're interested in divisibility by 5, because we're ultimately interested in divisibility by 45. So if, so we would say like AN is divisible by 5 when n equals 4 plus 5 multiplied by, let's say, m, some number m, some integer. Okay, so we're looking for solutions like that. All right, now let's check 9. 9 doesn't show up as often, does it? That's why I really wanted to look at 3 to convince you that these patterns are very reliable. Our first divisible by 9 number was 10. And then we had to go 1, 2, we skip over 2 divisible by 3 numbers and get the next divisible by 9 number at 22. So we actually have to add 12 each time to find our next divisible by 9 number. So AN is divisible by 9 when n is equal to, our first one was at 10, plus 12, and let's say not m, but no, we could say 12p, okay, where m and p and m are of the integers, okay. All right, so now we've got that. Now we want to know what values of n will both this be true for some integer and this be true for some integer. In other words, when is the number both divisible by 9 and by 5? Okay, so we can do that by just equating those two things. 4 plus 5m is equal to 10 plus 12p. Okay, and then let's get that to be, 5m is equal to 6 plus 12p. And we don't need to factor that or anything like that. You just leave it alone. All right, now we're looking for some number that when we put it in there and there, we get an integer solution. And I can see, well, if p equals 2, then you have 6 plus 12 times 2 equaling 5 times m. Well, 6 plus 12 times 2 is 30 is equal to 5m, so that would mean like m equals 6. Okay, so when m equals 6, we are talking about the 34th term is one of these that's divisible by 5, but the 34th term is also divisible by 9. So the 34th term is the first one that's divisible by 45. And I didn't happen to build it out as far as I needed to show you that one, but I don't need to. I'm reliably like 100% certain that it is divisible by 45, and it's the first one. Now, when would the next one be if we have like, 5m equals 6 plus 12p? Well, when I've got this solution, I'm looking for how many solutions do we have here. Oh my goodness. Okay, so, my only cap is I'm looking at the first 25 terms in this sequence. So if like this n is greater than or equal to 2025, then we're done. We don't need to consider anymore. So I know that this will recur when I have the product of both coefficients. That is to say, if I know that mp equals like 6, 2, well, I could add 5 to that and 12 to that, and it would work. All right? So that is to say, if I do 18 and 7, that I'll find another solution. So let me just verify that for you. 5 times 18 is in fact 90, is equal to 6 plus 12 times 7, which is also 90. This is 6 plus 84, and this is 90. So this is the next time that they meet, and I just get that by, I know that if I increase p by 5, I'm increasing the same amount as if I increase m by 12, and that's actually the minimum amount. That's like a lowest common denominator, sorry, the lowest common multiple property there. The lowest common multiple of 5 and 12 is 60. So every 60th term after 34 will be a solution where the term squared will be divisible by 2025 because the term will be divisible by 45. Okay, so now we know this. 34 plus 60, we already used p, so let's use q. If this is less than or equal to 2025, we have ourselves a solution. Okay, so let's move over that 34. So let's do that. So we have 60q is less than or equal to 2025 minus 34, which is a fancy way of saying 1991. And then we divide both sides by 60. So 1991 divided by 60. 33. So Q must be less than or equal to 33. Okay, cool. So there's 33 answers. Don't forget the first one. Okay, this is 1. When Q is 0, that's still a solution. So we have 33 plus 1 equals 34 answers to this problem. Isn't that delightful? This is so delightful. Okay, let's take a look at all the things that they did. So 34 is the first term that was one of these terms where its square was divisible by our year number, and 34 is Fibonacci, and we already know that they love Fibonacci numbers. So I hope that explanation was to your liking. If you wanted to see anything more about these like recursive patterns and their divisibility by different numbers, take a look at the factors of the Fibonacci numbers and you will find the same patterns at work there. So you go like 1, 1, 2, 3, 5. So 5 is the fifth term and it's the first one divisible by 5. 8, 13, 21, 34, 55. So 55 is the 10th term and it's also divisible by 5, and so on and so on. The next one will be 610 is the next divisible by 5 one, and that must be the 15th Fibonacci term because every 5 are divisible by 5. This has this pattern. And then divisible by 3. 1, 1, 2, 3. 3 is the fourth Fibonacci term and it's divisible by 3. 5, 8, 13, 21. Oh, that's the 8th one, and it's also divisible by 3. So they all have this pattern. And because Fibonacci, like the 0 term starts on 0, all of like, you don't have this kind of toggling its divisibility sort of along the pattern in some way. It always starts at like a nice round number. So it's very cool. All right, I hope that that was to your liking, and any questions, hit me up by the comments. Bye for now.